Graph theory is a growing area in mathematical research, and has a large specialized vocabulary. Some authors use the same word with different meanings. Some authors use different words to mean the same thing. This page attempts to describe the majority of current usage. Basics. A graph G consists of two types of elements, namely vertices and edges. Every edge has two endpoints in the set of vertices, and is said to connect or join the two endpoints. An edge can thus be defined as a set of two vertices. The two endpoints of an edge are also said to be adjacent to each other. Alternative models of graphs exist, e.g., a graph may be thought of as a Boolean binary function over the set of vertices or as a square matrix. A vertex is simply drawn as a node or a dot. The vertex set of G is usually denoted by V, or V when there is no danger of confusion. The order of a graph is the number of its vertices, i.e., V. An edge is drawn as a line connecting two vertices, called endpoints or end vertices or end vertices. An edge with end vertices x and y is denoted by xy. The edge set of G is usually denoted by E, or E when there is no danger of confusion. An edge xy is called incident to a vertex when this vertex is one of the endpoints x or y. The size of a graph is the number of its edges, i.e., E. A loop is an edge whose endpoints are the same vertex. A link has two distinct end vertices. An edge is multiple if there is another edge with the same end vertices, otherwise it is simple. The multiplicity of an edge is the number of multiple edges sharing the same end vertices. The multiplicity of a graph. The maximum multiplicity of its edges. A graph is a simple graph if it has no multiple edges or loops, a multigraph if it has multiple edges but no loops, and a multigraph or pseudograph if it contains both multiple edges and loops. When stated without any qualification, a graph is usually assumed to be simple, except in the literature of category theory, where it refers to a quiver. Graphs whose edges or vertices have names or labels are known as labeled, those without as unlabeled. Graphs with labeled vertices only are vertex labeled, those with labeled edges only are edge labeled. The difference between a labeled and an unlabeled graph is that the latter has no specific set of vertices or edges. It is regarded as another way to look upon an isomorphism type of graphs. To the edges and vertices of a graph, subject to certain rules depending on the situation. This should not be confused with a graph merely having distinct labels or names on the vertices. A hyperedge is an edge that is allowed to take on any number of vertices, possibly more than two. A graph that allows any hyperedge is called a hypergraph. A simple graph can be considered a special case of the hypergraph, namely the two-uniform hypergraph. However, when stated without any qualification, an edge is always assumed to consist of at most two vertices, and a graph is never confused with a hypergraph. A non-edge is an edge that is not present in the graph. More formally, for two vertices M is a non-edge in a graph whenever is not an edge in. This means that there is either no edge between the two vertices or at most one of and from is an arc in G. Occasionally the term cotriangle or antitriangle is used for a set of three vertices none of which are connected. The complement of a graph G is a graph with the same vertex set as G but with an edge set such that xy is an edge and if and only if xy is not an edge in G. An edgeless graph or empty graph or null graph is a graph with zero or more vertices but no edges. The empty graph or null graph may also be the graph with no vertices and no edges. If it is a graph with no edges and any number of vertices, it may be called the null graph on vertices. A graph is infinite if it has infinitely many vertices or edges or both, otherwise the graph is finite. An infinite graph where every vertex has finite degree is called locally finite. When stated without any qualification, a graph is usually assumed to be finite. See also continuous graph. Two graphs G and H are said to be isomorphic, denoted by G tilde H, if there is a one-to-one correspondence, called an isomorphism, between the vertices of the graph such that two vertices are adjacent in G if and only if their corresponding vertices are adjacent in H. Likewise, a graph G is said to be homomorphic to a graph H if there is a mapping, called a homomorphism, from V to V such that if two vertices are adjacent in G then their corresponding vertices are adjacent in H. Subgraphs. A subgraph H of a graph G is a graph whose vertices are a subset of the vertex set of G, and whose edges are a subset of the edge set of G. In reverse, a supergraph of a graph G is a graph of which G is a subgraph. A graph G contains a graph H if H is a subgraph of or is isomorphic to G. A subgraph H spans a graph G and is a spanning subgraph or factor of G if it has the same vertex set as G. A subgraph H of a graph G is said to be induced if, for every pair of vertices X and Y of H, XY is an edge of H if and only if XY is an edge of G. In other words, H is an induced subgraph of G if it has exactly the edges that appear in G over the same vertex set. If the vertex set of H is the subset S of E, then H can be written as G, S, and is said to be induced by S. A graph G is minimal with some property P, provided that G has property P and no proper subgraph of G has property P. In this definition, the term subgraph is usually understood to mean induced subgraph. The notion of maximality is defined dually. G is maximal with P provided that P and G has no proper supergraph H such that P. A graph that does not contain H as an induced subgraph is said to be H-free, and more generally if is a family of graphs then the graphs that do not contain any induced subgraph isomorphic to a member of are called free. For example, the triangle-free graphs are the graphs that do not have a triangle graph as an induced subgraph. Many important classes of graphs can be defined by sets of forbidden subgraphs. The graphs that are not in the class and are minimal with respect to subgraphs, induced subgraphs, or graph minors. A universal graph in a class K of graphs is a simple graph in which every element in K can be embedded as a subgraph. Walks. A walk is a sequence of alternating vertices and edges, beginning and ending with vertices, where each edge's endpoints are the preceding and following vertices in the sequence. A walk is closed if its first and last vertices are the same, and open if they are different. The length L of a walk is the number of edges that it uses. For an open walk, L equals n1, where n is the number of vertices visited. For a closed walk, L equals n. In the example labeled simple graph is an open walk with length 5, and is a closed walk of length 5. A trail is a walk in which all the edges are distinct. A closed trail is sometimes called a tour or circuit, but these usages are not universal, and the latter is often reserved for a regular subgraph of degree 2. Traditionally, a path referred to what is now usually known as an open walk. Nowadays, when stated without any qualification, a path is usually understood to be simple, meaning that no vertices are repeated. In the example labeled simple graph is a path of length 2. The closed equivalent to this type of walk, a walk that starts and ends at the same vertex but otherwise has no repeated vertices or edges, is called a cycle or closed path. Like path, this term traditionally referred to any closed walk, but now is usually understood to be simple by definition. In the example labeled simple graph is a cycle of length 3. Paths and cycles of n vertices are often denoted by Pn and Cn, respectively. C1 is a loop, C2 is a dig-in, and C3 is called a triangle. A cycle that has odd length is an odd cycle, otherwise it is an even cycle. One theorem is that a graph is bipartite if and only if it contains no odd cycles. A graph is acyclic if it contains no cycles, unicyclic if it contains exactly one cycle, and pancyclic if it contains cycles of every possible length. A wheel graph is a graph with n vertices, formed by connecting a single vertex to all vertices of Cn1. The girth of a graph is the length of a shortest cycle in the graph, and the circumference, the length of a longest cycle. The girth and circumference of an acyclic graph are defined to be infinity. A path or cycle is Hamiltonian if it uses all vertices exactly once. A graph that contains a Hamiltonian path is traceable, and one that contains a Hamiltonian path for any given pair of n vertices is a Hamiltonian connected graph. A graph that contains a Hamiltonian cycle is a Hamiltonian graph. A trail or circuit is Eulerian if it uses all edges precisely once. A graph that contains a Eulerian trail is traversable. A graph that contains a Eulerian circuit is a Eulerian graph. Two paths are internally disjoint if they do not have any vertex in common, except the first and last ones. A theta graph is the union of three internally disjoint paths that have the same two distinct n vertices. Some authors have used the term theta-zero graph to refer to a graph that has 7 vertices and 8 edges that can be drawn as the perimeter and 1 diameter of a regular hexagon. The smallest, excluding multigraphs, topological minor of a theta-zero graph consists of a square plus one of its diagonals. Trees. A tree is a connected acyclic simple graph. For directed graphs, each vertex has at most one incoming edge. A vertex of degree 1 is called a leaf, or pendant vertex. An edge incident to a leaf is a leaf edge, or pendant edge. A non-leaf vertex is an internal vertex. Sometimes, one vertex of the tree is distinguished, and called the root. In this case, the tree is called rooted. Rooted trees are often treated as directed acyclic graphs with the edges pointing away from the root. A subtree of the tree T is a connected subgraph of T. A forest is an acyclic simple graph. For directed graphs, each vertex has at most one incoming edge. A subforest of the forest F is a subgraph of F. A spanning tree is a spanning subgraph that is a tree. Every graph has a spanning forest, but only a connected graph has a spanning tree. A special kind of tree called a star is K1, K. An induced star with 3 edges is a claw. A caterpillar is a tree in which all non-leaf nodes form a single path. A Kary tree is a rooted tree in which every internal vertex has no more than K children. A 1Ary tree is just a path. A 2Ary tree is also called a binary tree. Cliques. The complete graph not of order n is a simple graph with n vertices in which every vertex is adjacent to every other. The pentagon-shaped graph to the right is complete. The complete graph on n vertices is often denoted by knots. It has two edges. A clique in a graph is a set of pairwise adjacent vertices. Since any subgraph induced by a clique is a complete subgraph, the two terms and the notations are usually used interchangeably. A K-clique is a clique of order K. In the example labeled simple graph above, vertices 1, 2 and 5 form a 3-clique, or a triangle. A maximal clique is a clique that is not a subset of any other clique. The clique number omega of a graph G is the order of a largest clique in G. Strongly connected component. A related but weaker concept is that of a strongly connected component. Informally, a strongly connected component of a directed graph is a subgraph where all nodes in the subgraph are reachable by all other nodes in the subgraph. Reachability between nodes is established by the existence of a path between every pair of nodes in the component. A directed graph can be partitioned into strongly connected components by running the depth-first search algorithm twice. First on the graph itself and next on the transpose graph in decreasing order of the finishing times of the first DFS. Given a directed graph G, the transpose GT is the graph G with all the edge directions reversed. Hypercubes. A hypercube graph is a regular graph with 2n vertices, 2n-1n edges, and n edges touching each vertex. It can be obtained as the one-dimensional skeleton of the geometric hypercube. Knots. A knot in a directed graph is a collection of vertices and edges with the property that every vertex in the knot has outgoing edges, and all outgoing edges from vertices in the knot terminate at other vertices in the knot. Thus, it is impossible to leave the knot while following the directions of the edges. Minors. A graph is a minor of a graph if can be obtained from by a sequence of edge deletions, isolated vertex deletions, and edge contractions that merge the two endpoints of an edge as a single vertex. A related concept is topological minors, whereas a topological minor of if there is an injection from to such that every edge in corresponds to a path in. Embedding. An embedding of is an injection from to such that every edge in corresponds to a path in.